we jump right in? We're going to take a look at how we might model the game of Battleship in Python. In order to get started, I'll share my screen with you. Behind me, you should see my screen. I'll, of course, hide in the corner here. Let's take a look. Well, before we get started talking about the game of Battleship, one thing that might be interesting for us to discuss is why it is that these games show up so often when we're showing people all of what Python can accomplish. And the reason is that many games have a very fixed model, and given that fixed modeling, the fixed set of rules, the agreement that everybody knows how this game is played and how this game will be won, well, we might see different features of the language show up in very nice, terse fashion. One such feature is object orientation. But before we show you even the most naive approach for modeling the game of Battleship, let's give a very brief review of object orientation as it appears in Python. Because typically, when we talk about object orientation, we're often talking about encapsulating behavior together with state. And here you can see a canonical view of an object that has some internal state that we're not supposed to manipulate directly, but instead we're supposed to manipulate by calling methods on this object, inc and dec, to increment and decrement the state. And of course, when we run through this, we can see that from the outside of this object, we can tell it what we want it to do. But we are encouraged not to directly manipulate it. We are encouraged never to do an object.state change like that. Now, it may be the case that in order to make it a little bit clearer that we're not supposed to pierce that veil, this might have just some special naming associated with it, a single underscore. Or we might even use something like a property and a closure or some other mechanism to try to hide this. But for the most part, when we talk about object orientation in Python, this is largely what we're talking about. It may be the case that we do not maintain that encapsulation that directly or that aggressively. It may be the case where we say, for the most part, let the object handle incrementing and decrementing. But, in some cases, we understand that you might want to do a reset operation that isn't already implemented, and you might touch the state, or you might just want to look at it for debugging purposes. Now, when we talk about object orientation in Python, one thing that is not always clear is what really constitutes object orientation in Python, because we know that for the most part, the language is pretty thoroughly object oriented, to the degree that when we take a look at, say, a built-in type, like just the number 0, we can see that there are methods on this type, like bit length. How many bits does it take to represent this value, 0? And in fact, every entity that we can interact with in Python is an object of some sort. To the Python interpreter, every entity that we can interact with, every built-in type, every integral object, is a PyObject pointer for your CPython interpreter. This is unlike some programming languages like Java, where we have a distinction between elemental types and object types, value types, and reference types. In Python, everything's an object and everything has methods. So is it possible for us to not use object orientation in Python? Well, I would say that most people would agree that some code that looks like this doesn't constitute object-oriented code. Here we have some data and we have some methods that apply to that data. We have the exact same functionality as before, but we've structured that functionality slightly differently. And if somebody says, you shouldn't be using objects in Python as much as you are, or you should be using objects in Python differently, they probably mean that you should be writing your code in this fashion. Just regular functions that sit in some module, perhaps still sit in some namespace, and instead of operating on some encapsulated state, they take all of their arguments and then just return some value. Now, if we take the same example and we extend it very slightly, for example, we use a built-in data type. So x is no longer just the value 1, 2, 3, but it's a list of the increment operation, the decrement operation, and the 1, 2, 3 operation. Because again, everything that we interact with in Python is an object up to and including things like these functions, which have methods and have properties on them like any other. We can ask, for example, this function what its name is, or if it has any default values, we can ask it for that. We can even look and see what behind the scenes the bytecode of this function actually looks like. But if we were to do something like this and only very minorly change this example, I think most people would say that the use of the built-in types, despite them very clearly being objects, doesn't really count as an object-oriented approach. Or to put it another way, when somebody tells you don't use an object-oriented approach in this particular portion of your code, they don't mean, well, don't use anything that's a built-in type, just use integers and strings. I'm sure that they would say it's fairly reasonable for us to use a list, a set, a dictionary, which themselves are objects and have methods. Or maybe even a subclass of those, which again are objects which have very interesting methods. Well, if we were to take that same example and we were to extend it very slightly, and we're to say referring to the increment and the decrement by their index is so clumsy that instead I'd like to name those fields. I'll use a tuple, or more specifically, I'll use a collections.name tuple. It is very much the case behind the scenes. Somebody is creating a new type, and that new type is being created with all of those methods that we identify as being part of object orientation in Python, an init, a repr, and so forth and so on. But when you look at this, this is just barely different than if somebody just used a tuple and referred to these fields by their position. And so I would say most of the time when people talk about the use of a named tuple, they're talking about very light object orientation, or maybe not even considering that to be object orientation at all. In fact, if we look at a couple of choices and we try and say, well, where is the line between object orientation and the non-object oriented approach, we would almost certainly draw that line before choice number 4 or in choice number 5. It is absolutely the case that when you write that class keyword, that's definitely going to be object orientation. If you use a boilerplate elimination tool like data classes.data class, most people would say, you know what, you're still writing that class keyword, and all that data class is doing is filling in a lot of the details that are so rote, so similar between the different types of classes that you might create that we just want to eliminate that boilerplate, do a little bit of metaprogramming, make our life a little bit easier, make our code a little bit terser. But that's still object orientation. So almost everybody would say 4 and 5, object orientation, absolutely no doubt. 3 is probably the point where most people would say, you know, maybe we're touching upon object orientation, but largely this is just some kind of data structuring. This doesn't really count. That is to say, number 3 and number 4 seem to be materially different because it's very common that in number 4, we might add some additional methods. But if we were to do the same thing here, well, we can add methods. We can subclass this and we can add methods to it, but this seems to be a rarer occurrence. And so 3 is just about where we'd say, you know, maybe that's not really the object-oriented approach. It's just some basic data structuring. Obviously, 1 and 2, just the use of some elemental data with different variable names or the use of some built-in type like a tuple. Most people would say, you know what, we know those are objects, but there is a materially different approach when you have functions that just take some kind of structured data versus when you encapsulate things in objects. Now, having litigated that so finely for you, why don't we talk a little bit about, well, when do we actually need to do the furthest forms of object orientation, the forms that involve, say, the data classes.data class, or writing a class and all of those underscore methods ourselves. It turns out that as a consequence of Python having first-class functions with closures, one of the main reasons for which we would write that class keyword and use object orientation is not something that we are required to do in Python. In other words, if we had our incrementer and decrementer that we'd write in this very firmly object-oriented style, well, we can get the exact same behavior by just writing a function that returns new functions, where these new functions close over some non-local state. And if we take a look at the output of these two programs, they are identical. These two formulations, these two styles of writing the exact same idea are identical in functionality, even though you can see syntactically, well, okay, yeah, this is using some sort of indexing and this is using some sort of dotted access. One of them is definitely preferable to the other. One of them is definitely more clumsy than the other. However, since we kind of agree that a named tuple doesn't really count as object orientation, nothing really stops us from making these two examples almost identical. And in fact, we've discovered something very interesting here. When we talk about object orientation as basic data structuring, putting things into a particular structure to make it easy to work with, adding names to fields, well, that is something that requires some object orientation, but to a large degree, that's not the most interesting thing. And the interesting thing about object orientation, that encapsulation, can be achieved through two distinct means. Either closing over some environment when you're defining a new function dynamically, or via the classical class with an init method and all the other underscore method approach. And if we dig slightly under the covers, we will see that the correspondence is actually quite close indeed. Because if we look at the classical approach of writing an object and we dig into this thing, we will see that it stores its instance state in a special dictionary that is located under _dict. Now, of course, this isn't always guaranteed to be the case. We could have something with slots, and in the presence of slots, we no longer have that field. But this is really just an optimization that doesn't really affect the semantics. It's definitely the case that we don't want to ever do anything with this dict because we don't know if it's going to be present or not. But we can see that this is some detail of how this object is being represented internally to the interpreter. And interestingly enough, if we were to take a look at our closure approach, and we were to dig under the covers, we were to look at just one of these functions, we would see that it has an _closure field. And in that closure field, it has a tuple of cells. And in one of those cells, it has the contents representing the state of the object at any point in time. In these cases, we are basically representing the same data in pretty much two different ways, either as a dictionary with the name of the attribute mapped to its value, or as a closure with a tuple of cells that we can set and retrieve the contents of. And of course, the reason why we have this difference is in the object, whenever it does self.state, it's dynamically looking up that field. This self.state operation is the equivalent of doing a dictionary lookup into the special dictionary with that special key. Whereas, when we use the closure approach, Python generates bytecodes for every reference to this state variable. And when it generates those bytecodes, it knows the fixed location in this closure tuple where it's going to find that. And so behind the scenes, it's just turning this into something like a tuple access or a list access, an indexed access. But beyond that, very superficial detail, we can see a very close correspondence between these two approaches, which means if we want the benefits of encapsulation, taking some state together with some behavior and giving us the ability to manipulate that state without manipulating it directly, but instead through the interface of that behavior, we have two distinct ways to do it. We do not need to write objects. We can instead write functions that return functions. We can instead use closures. This is, in fact, a very well-known dichotomy in computer science. Objects and closures are two sides of the same coin.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.